3. Okay, good. Somebody hit the recording button. Awesome. That's one thing I always forget to do. Okay, our first speaker is Masaki Oshikawa. And it's our job to ask a lot of interesting questions so he doesn't fall asleep giving his own talk. All right, go for it.
Okay, thank you. So it's great pleasure to give a talk for this symposium. And, I would have liked to visit New York City physically, but well, the online conference is better than being isolated. And at least I'm trying to be virtually in New York City. So today I like to talk about the generalized Kohn formula and some rules on nonlinear conductivities. And my talk is mostly based on my recent paper with Haruki Watanabe and another with Yankan Liu, who is Haruki's student. But I think I have given a talk on these topics a few times, so maybe some of you attended, but I hope I can cover some recent development, including this recent paper, not involving myself, but by Tanikawa, Taka-san, and Katsura, who extended our work. Actually, I found Taka-san and Katsura-san in the audience, so maybe if you happen to have detailed question on this last part, maybe we can ask them. Okay. So first about basic idea. So there is a very influential paper by Walter Kohn written in 1964. So he gave a basic formulation on how to distinguish insulator from conductor. Of course, insulator and conductor are distinguished by electric conduction property. But to be more precise, we can define conductivity as a function of frequency and wave number, which is nothing but the proportionality coefficient between the current density induced by electric field and the applied electric field. And in discussing this distinction between insulator and conductor, in particular, the quantity called Drude weight, we first focused on zero wave number component, that is uniform electric field and uniform current density as a response to the applied uniform field. Then now we set wave number to 0. Then this linear conductivity is now the function of frequency omega. Then generally this conductivity as a function of frequency omega is given by sum of regular part, which is some regular function of omega, plus possibly this 1 over omega singularity near omega equals to 0. So if you take a real part, this gives you a delta function of omega. And the coefficient of this singularity is called Drude weight. And in this paper, Kohn argued that the conductor can be characterized by non-zero Drude weight, whereas insulator is characterized by zero Drude weight, at least in zero temperature limit. And of course, the singularity is kind of only exists in the ideal limit. So in realistic system, this delta function singularity is often broadened by various factors. But if you consider ideal simplified model like lattice model, tight binding model, Hubbard model, this singularity does exist. And we can distinguish whether the given model is conductor or insulator by looking at the Drude weight. In other words, non-zero Drude weight is a signature of so-called perfect conductor. So in order to formulate this Drude weight, actually this was also done by Walter Kohn, but it's useful to introduce Aharonov bond flux. So we consider the system and impose periodic boundary condition, then we can regard the system as a link. So this is the X direction and it forms a link. Then there's a hole in the system where there is no electron accessing this hole, but you can put magnetic flux into this hole. Then this magnetic flux induces a vector potential inside this system like this, phi over length in X direction, Lx is the vector potential. Okay, so if you fix the value of flux, then even though this magnetic flux generates vector potential, in terms of classical mechanics, these particles don't go into this hole, so they don't touch this flux. So there should be no effect on the motion of particles. But in terms of quantum mechanics, this vector potential changes the pattern of interference that is called Aharonov-Bohm effect. So even static flux affects the quantum mechanical motion of particles on the link. But if you change the flux as a function of time, then even in classical mechanics, the change of flux induces the electric field in X direction, which can induce current. So we can consider this setup to discuss Drude weight and more generally conduction property of the electron system. So it's conventional to formulate Drude weight in terms of frequency space, frequency momentum space. But I found it also useful to formulate Drude weight in real time. So this is our formulation. So the current, uniform current at time t arises as a response to the electric field, uniform electric field applied to the system before time t. So we can define some real-time response function, sigma, which gives you how much current is induced after a certain time if you apply electric field pulse at a certain time. So the total current is given by this convolution form. So it's a kind of accumulation of all the response of the electric field applied in the past. And in this formulation, the Drude weight is nothing but the infinite time limit of this response function, sigma. So in words, if you apply electric field pulse at t equals 0, then you induce the current. But you may expect this current should decay over time. But sometimes this current survives even after infinitely long time. And how much current survives after infinitely long time is nothing but the Drude weight.
Masaki, can I ask a question?
Sure, yeah.
Can one still make sense of, is this definition still useful for, let's say, considering more realistic materials? I mean, it's not strictly useful, but is there still a distinction?
Yeah, I hope so, but I haven't tried to analyze the actual experiment very carefully, but sometimes. Well,
I just mean anything with momentum relaxation.
Yeah. Okay. Yeah. So of course, in realistic system, as I discussed in the previous slides, there are various relaxation mechanisms. So that's will kill this permanent current. But I think it's a matter of time scale. So if the relaxation time is very long, then up to that relaxation time, we can observe this.
But in practical terms, if there is a simple exponential decay of current, then simply measuring this amplitude, is that the amplitude of that exponential is the Drude weight, basically?
Yeah. If we can identify such a how to say long-term surviving component of the current, right, then yes.
Yeah, presumably everything else oscillates.
Yeah. But at least for idealized lattice model, this is I think still very defined. So in order to study this, we can consider this Aharonov-Bohm link and insert a flux. So you start from ground state, let's say, and t equals 0, and then switch on constant electric field. Then measure how much current is flowing as a function of time. So if you keep applying the constant electric field, then in the presence of Drude weight, actually the current grows linearly as a function of time. And this turns out to be useful relation. Okay. Yeah, sorry, I removed one important slide, but yeah, maybe I changed the order of the slide. Sorry about that. So this previous observation leads to this relation between current versus energy. That is, current operator is always given by derivative of Hamiltonian by vector potential and divided by volume, that's current density. So you can relate current to the derivative of Hamiltonian. So if you integrate both sides, then the integration of current is related to the increase of the energy. So in this way, if you add flux adiabatically, then over the time, you are applying the constant electric field. And how much energy is increased by insertion of flux is related to how much this permanent current is induced by electric field, which is proportional to the Drude weight. So the Drude weight and energy increase due to adiabatic flux insertion can be related. And actually, if you take the limit of small phi 0, so phi 0 is the Aharonov-Bohm flux I have introduced previously. The Drude weight is related to the second derivative of the ground state energy as a function of the Aharonov-Bohm flux. And that is nothing but the so-called Kohn formula, the famous Kohn formula, that gives you the Drude weight as a second derivative of the ground state energy by the vector potential or Aharonov-Bohm flux. And this formula, famous formula, was introduced in this seminal paper by Kohn in 1964. Okay, so in some sense, this real-time formulation so far just reproduced well-known Kohn formula for the Drude weight. But using this formulation, we can generalize this result.
Can you say, I mean,
yes.
that looks a lot like rho S in the superconductor?
Yeah, good question. So the Drude weight and rho S somewhat similar, but they distinguished. And yeah, so there are a lot of subtleties, and I have to say that I'm still trying to understand the true difference. But what Scalabino, White-Jan proposed was that superfluid density, superconducting weight or superfluid density should be defined in terms of conductivity sigma as a function of omega and q, and you fix q finite first, then consider the singularity near omega equals 0, and after that you take the limit of q equals 0, then you get superfluid density. But this Drude weight, you first set q equals 0.
I see.
Yeah, then Scalabino, White-Jan show the inequality that Drude weight is equals to or bigger than superfluid density, which makes sense. Yeah.
Okay.
So here I start from q equals 0. So I'm not discussing superfluid density, but only Drude weight.
Okay, thanks.
Yeah. So before going into the generalization actually to nonlinear derivatives, I want to comment about what happens if you insert so-called unit flux quantum, that is HC over E in standard unit. If you define H bar equals to C equals to E equals to 1, then unit flux quantum is 2 pi. And this unit flux quantum 2 pi exactly means that the quantum mechanical phase acquired by electron when electron goes around this link is exactly 2 pi. And when the Haranoff-Bohm effect gives you phase 2 pi, the phase 2 pi is equivalent to 0 phase. So when you apply unit flux quantum exactly, that is 2 pi, then there is no Haranoff-Bohm effect. So for electrons living inside the link, you don't feel any effect of flux if the inserted flux is unit flux quantum. So it's interesting to consider what happens if you adiabatically insert exactly this unit flux quantum 2 pi. Then the ground state evolves from original ground state to some other state, which I don't know generally what it is, but there must be some finite state. So this is generally different from the original ground state. And also after inserting the unit flux quantum, the Hamiltonian acquires a vector potential gauge field. So it's different from original Hamiltonian with 0 flux. But because Haranoff-Bohm effect basically vanishes for 2 pi flux, so we can eliminate the unit flux quantum by doing so-called large gauge transformation. So there is a certain operator which changes quantum mechanical phase of the wave function around the system, and the phase change goes from 0 to 2 pi. So it's a topologically non-trivial gauge transformation by which you can eliminate 2 pi flux. Then Hamiltonian goes back to the original Hamiltonian. So in that sense, Hamiltonian with 2 pi flux is equivalent to original Hamiltonian. That makes sense because there is no Haranoff-Bohm effect. But the states can evolve into different states. So first you started from ground state and evolved into some other state by adiabatic flux insertion. Then in order to go back to the original Hamiltonian, you need to apply this gauge transformation. So the wave function also changes. So this is a final state after adiabatic evolution plus large gauge transformation. And this final state may be different from the original ground state in general.
What is that of R, n sub r?
Sorry.
In this formula, n sub r.
Ensemble. Sorry, I didn't give you the definition. So I was imagining like a lattice model, like a Hubbard model. Then NR is just a number operator of particle at site R.
Oh, I see.
Yeah.
Oh, so this just shifts the phase by X.
Yeah.
Thank you.
So this is just adding some introducing extra phase to wave function, but this extra phase is proportional to X. Yeah. Sorry about that. Yeah.
And X is goes around the circumference.
Yeah. So X goes from 0 to Lx minus 1 or something like that. Yeah.
Okay.
Yeah. Then this is consistent with periodic boundary condition because X equals to Lx is equivalent to X equals to 0 because of this is a phase. Yeah. Okay. So yeah, that's a setup. Then now I want to discuss extension generalization of famous Kohn formula for linear conductivity or linear derivative. And so for that, I want to discuss nonlinear conductivities. So nonlinear conductivity just means that I measure the current And often you focus on linear response, that is current linear in applied electric field. But if you apply especially strong electric field, then in principle there are higher order response of the current to the electric field. So there should be current component of the current which is proportional to E squared or E cubed and so on and so on. And in terms of real-time formulation, we can again express the current at time t as accumulation of response to the electric fields applied in the past. So current density at time t is given by this kind of integral, which is proportional to electric field strength at time t1, t2, t3 up to tn. And then you multiply with this linear, real-time response function, then integrate over all t1, t2, t3 from -infinity to time t because of the causality. So you can always define this. Then similarly to the linear response, linear conductivity, and then standard Drude-Waite, we can also define nonlinear Drude-Waite by considering the limit of this real-time response function and taking all these time delay to infinity. So yeah, this may be finite or maybe zero, but by this we define Drude-Waite, nonlinear Drude-Waite at nth order. So by defining this quantity, we can use the same trick as before, which I used to derive the Kohn formula for linear Drude-Waite. That is, if we assume that there is non-vanishing nonlinear Drude-Waite dn, then if you do this integral for constant electric field, and if for large time delay there is this constant contribution to this real-time response function, then you can actually integrate this formula to obtain the most dominant part. And the dominant contribution due to the nonlinear Drude-Waite is proportional to t to the power n, and also this vector potential to the power n. But I have derived a general identity between the energy increase to the this integrated current. So we can also use this relation for nonlinear response of the current, and then compare each side of this identity order by order. Then what we find is simply that this nth order nonlinear Drude-Waite is related to the higher order derivative, n+1 derivative of the ground state energy with respect to the vector potential. So if you said yes.
Oh, can I ask a question? Because in principle, I think to this order, you might have sort of nonlinear effects. So suppose AX doesn't turn like completely linearly. I think you'll get contribution like AX dot squared, which will be exactly of the same order. I just wonder if it's sort of like what you have is velocity squared, right? If I think about AX over t initially. And you can have now velocity, say power of 4, if n is equal to 4, but you can also have acceleration squared, and they're exactly of the same order. I just wonder if this plays any role anywhere.
So you are assuming some form of Hamiltonian, or?
Yeah, so if AX is not just exactly a linear function of time, because adiabatic
I see. Okay. Yeah, so for simplicity here, I assume that this vector potential is increased linearly in time, but actually to derive most number of results, it is useful to consider more generic increase of vector potential as a function of time. And yeah, I forgot exactly, but yeah, basically by considering arbitrary increase of vector potential as a function of time, we can derive this relation and even more. Yeah.
So the fact that acceleration at time equals to 0 becomes infinite in this protocol doesn't play a role, right? Because it's very tricky. To the previous order, everything was fine, but here it's a little bit subtle.
Actually, I admit that this is kind of subtle business, and actually, I will show some, some evidence that this quantity is actually subtle. But in a very formal level, I think we can define this quantity, and maybe we can discuss later after I show you some very tricky result. Actually, yes, but yeah, I agree that this is kind of tricky business. Yeah. Okay, so yeah. So that was derivation of the nonlinear, the Kohn formula generalization to nonlinear Drude-Waite. And I want to mention quickly about the other limit. That is, in order to derive the Kohn formula for Drude-Waite, nonlinear Drude-Waite, I used the adiabatic insertion of Aharonov-Bohm flux. But we can also consider the other limit, that is a sudden insertion of Aharonov-Bohm flux. So I can use the same formula, for example, that is, I increase the vector potential linearly over time for the period from t equals 0 to capital T. But the adiabatic insertion corresponds to the limit, this capital T goes to infinity. But I can also discuss the opposite limit, taking this capital T to 0. That corresponds to sudden insertion flux or some sort of quantum quench, right? And physically, this corresponds to delta function electric field pulse. But if you do this, basically you can apply the sudden approximation of quantum mechanics you can find in textbook. That is, if you change Hamiltonian instantly, then the wave function cannot catch up. So after t equals to plus epsilon, the wave function is still the original ground state. But important point is that, as I discussed in the case of unit flux quantum insertion, if you insert unit flux quantum instantly, suddenly, then wave function doesn't change. But the Hamiltonian changes by the vector potential. Then you can eliminate this inserted unit flux quantum by large gauge transformation. Then Hamiltonian goes back to the original Hamiltonian. But when you do this large gauge transformation, you should also transform wave function. So even though the insertion is instantaneous, sudden insertion, if you combine with this large gauge transformation, the wave function is changed from the original ground state to large gauge transformation applied to the original ground state. But we can again apply the same trick relating the integration of current to the increase of the
Masaki, can I just ask a question?
Yeah.
So in the sudden one, it's a bit confusing because it seems that the to do this gauge transformation, you know what the gauge is, but if you're just applying an instant, how do you even know what the gauge is to know what gauge transformation to undo?
Yeah, good point. So actually, unless the inserted flux is exactly integral multiple of unit flux quantum 2 pi, you cannot really eliminate the inserted AB flux. And actually, this discussion of Drude-Waite and also the F-sum rule I'm going to derive, you don't really have to use the unit flux quantum, you can just insert any fractional amount of flux and still apply this relation between energy increase to the integration of current. But yeah, I just thought that it's illuminating to consider the case of unit flux insertion. But maybe it's rather confusing. So maybe short answer is that actually you don't, for the purpose of today's talk, actually you don't really have to do the gauge transformation. But sometimes it may help understanding what's going on. Yeah, because yeah, this sudden insertion, yeah, this insertion of flux is a bit, yeah, subtle, sometimes counterintuitive because of this gauge invariance. But yeah, when you happen to insert exactly 2 pi flux, you can eliminate this flux. But in that case, you have to apply the gauge transformation. Yeah, sorry, maybe I'm not really answering your question, but short answer is that yeah, you don't really have to use this gauge transformation. Just use the identity between the energy increase versus integration of current. Is that okay? Or,
No, yeah, thank you. I should let you
yeah,
go on.
sorry, yeah, sorry. So yeah, I can use the same trick relating this energy increase and integration current. And I can also use this identity for the limit of sudden insertion, capital T goes to 0. And in this case, what I find is that, yeah, because I take the limit of T goes to 0, I pick up the this real-time response function in the limit of 0 time delay. So I set all the time difference to 0. And this response function is related to how much energy is increased. And how much energy is increased is given by this difference, because the new wave function is u psi 0, and old wave function is psi 0, and you take the difference. Or you just consider simply the difference between Hamiltonian with flux minus Hamiltonian with 0 flux, and then take ground state expectation value. But for the case phi 0 is 2 pi, this is equivalent to variational energy appearing in the proof of original Lipschutz-Matisse theorem, if you are familiar with. Okay, if you are not familiar with, you can forget about this Lipschutz-Matisse. But anyway, I can increase this energy increase to the response function conductivity at 0 time delay. And this conductivity at 0 time delay, if you go to frequency space, is given by frequency integral of conductivity as a function of frequencies. And this frequency integral is given by expectation of the derivative of higher order derivative of Hamiltonian with respect to the vector potential, then take ground state average. So this frequency integral is given by this quantity. And this is nothing but F-sum rule. So in particular, if you go to n equals 1, this is very well known F-sum rule of conductivity. But in this way, you can naturally generalize the F-sum rule for nonlinear component of the conductivity in a similar way. And resulting expression is actually pretty simple. And this looks like a Drude formula, but it's different. Yes.
So I had a question about
Yes.
what you're doing, I think.
Uh-huh.
So you're like this sudden insertion of flux, like as
Yeah.
you've explained, it is just like a gauge transformation, right?
Mm-hmm.
So how can there be any kind of response, right? Like you just like perform the gauge transformation. nothing physical should change. So like, why
Well,
are you getting something out?
well, no, yeah, actually, yeah, okay, so that's yeah, important point. It's a bit confusing, but the point is that so I start from ground state and then insert flux suddenly. Then because Hamiltonian changes suddenly, the ground state doesn't change. So you might say, okay, nothing changed, but actually Hamiltonian went to the different case. So actually physically, the physical state has already changed at this point because Hamiltonian went to the different case. And the final step is, okay, but I don't see how much the state is changed. So let's go back to the original case. Then you apply the large gauge transformation. Then Hamiltonian goes back to the original gauge and wave function is transformed to this u times psi zero. So then after this gauge transformation, Hamiltonian went back to the original gauge. Then the wave function is given like this. Then you can compare this state with the original ground state. Then you can see, okay, the state has indeed changed.
Okay,
Right.
but if that change is related by a gauge transformation, then like, why can it have like a different energy or like a different expectation?
Well, yeah, that's okay. I try to explain, but so the actual physical change already happened here because you inserted the flux suddenly. So that physically amounts to applying the delta function electric field pulse. So already at this stage, physically the state has changed. But if you just look at the wave function, it looks like there is no change. But it's kind of artificial because the Hamiltonian went to the different gauge. So if the wave function doesn't change, but the gauge has changed by flux insertion, then physically the physical state has already changed.
Is it that rather than like just making a gauge transformation, you're imagining like doing this adiabatic procedure that you were talking about just faster and faster? Is that the resolution? That, like, it's not just that you've done like a trivial change to your Hamiltonian.
Yeah.
Like
you can. Yeah, so I can start from finite t and go to t goes 0.
Okay. All right.
Yeah, and actually, yeah, another interesting point is that if you consider static problem, if you have AB flux inside a ring phi, then you can take. So there is a gauge degree of freedom. So you can take uniform vector potential AX constant to represent this flux phi, or you can introduce vector potential only in the single link of the lattice model, let's say tight binding model, Hubbard model. And as far as static problem, constant flux is concerned, this uniform vector potential and vector potential concentrated in the single link are completely equivalent. They are related by gauge transformation. But if you consider this dynamical problem, especially in the sudden limit, these two gauges give different physics because if you change the vector potential in the single link from 0 to 2 pi, then you are not doing anything. But if you use uniform vector potential and then suddenly change the total flux from 0 to 2 pi, then you do apply the electric field. So yeah, there are many.
Can I point out that we're running over time? So if there are questions, maybe we should postpone them to the breakout session later.
Okay. Yeah. Then sorry. So maybe I should quickly go to the. Okay. So my point is that I can derive the nonlinear generalizations of the Kohn formula and the F-sum rule in a unified way, and the result turned out to be very compact, rather compact expression. But there are subtleties. Okay, so let me skip this part. And we did check this formula in the tight binding model, but you might think it's kind of trivial for free fermion system. So let me just briefly mention some interesting results for spin 1/2 XXG chain. So this can be also regarded as spinless fermion in one-dimensional chain with density interaction given by this SG. And this model, of course, has been studied a lot by Bethe-Ansatz technique. I think there are experts on this subject in the audience. And in the low energy limit, this can be described by free boson effective field theory, also known as Tomonaga-Tinjari-Git. Then we can obtain the ground state energy density as a function of the flux of vector potential. And in fact, obtain these coefficients exactly. And of course, a linear Drude weight has been known for a long time. So this exact expression I'm not showing here, but you can obtain exactly and matches with numerical result as well. But we can also obtain the third order exact Drude weight based on some remarkable paper by Lukianov combining Bethe-Ansatz plus field theory between 98. And we can extract this third order Drude weight formula, which is plotted here, which agree with the numerical result very well, which is nice. But actually, this exact curve shows a divergence near this delta anisotropy parameter equals to -1/2. So it's puzzling. And actually, I mentioned, so there is a recent paper by Tanikawa, Takasan, Katsura, two of them are in the audience, it seems. So they further extended this kind of calculation to even higher order and more general cases. And this is an expression for fifth order nonlinear Drude weight. And this diverges in even wider range of parameters, that is delta less than 0 in our parameterization. Okay, so there is a, unfortunately, we use different conventions. So in their paper, this diverges for positive delta. Anyway, it diverges for anti-fermionic region. So yeah. So we find, yeah, we can define nonlinear Drude weight, and in some 1D system we can even calculate this exactly, which is nice, but they show some divergence in some range of parameter, which is rather mysterious. But it does not imply that the current response actually diverges, I think, because one reason is that so far, maybe correct me if I'm wrong, but so far what we know as examples of this diverging nonlinear Drude weight, they all show divergence to negative infinity. So it's not like this negative, divergent nonlinear Drude weight shows any actual divergence of the current, but rather the limit of the linear growth of the current as a function of time. So if you apply constant electric fields, then currents start to grow linearly within linear response regime, but eventually hit some limit. And perhaps this nonlinear Drude weight divergence shows this rather limitation of the current growth. And also, this in this paper, they showed nicely that this divergence of nonlinear Drude weight can be understood in terms of perturbed conformal field theory. And yeah, if you expand ground state energy as a function of flux, as a function of Aharonov flux and the system size, then there is some singular term which come from the irrelevant perturbation to the conformal field theory, Tomonaga-Tinjari-Git, and they showed how to understand this behavior by perturbed CFT. And the one nice consequence is that, so actually they come from so-called Umklapp terms in Tomonaga-Tinjari-Git theory. So if you apply magnetic fields, then you can make those Umklapp terms incommensurate, and effectively you can kill off the effects of these Umklapp terms. And in fact, so for in the presence of magnetic fields, I think we don't have any analytic exact formula, but numerically they can study this nonlinear Drude weight. And indeed, by applying magnetic fields, you seem to suppress this divergence of nonlinear Drude weight. Okay. So let me summarize. So by considering the very simple Gedanken experiment, thought experiment of inserting random flux into the ring, either adiabatically or suddenly, in these two limits, we can derive F-sum rule and Kohn formula for Drude-Waite, which are well known for linear response, but naturally we can extend these to nonlinear responses. And as you can see, two formulas look very similar, but are indeed different. So in the Kohn formula for Drude-Waite, you take derivative of ground state energy as a function of flux or vector potential. But in F-sum rule, you consider Hamiltonian as operator as function of vector potential, and then take derivative. And after taking derivative, you take ground state expectation value. So they are different. So those formulas are nice, but as pointed out, this formula seems rather tricky. And one indication of its tricky nature is in actual divergence of this nonlinear Drude-Waite in certain 1D exactly solvable system. And yeah, honestly, I don't fully understand its physical meaning. So these results are relatively new. So I think we should study these quantities more to obtain better understanding. Yeah. Sorry for going over time, but thanks for your questions and attention. Thanks.
I think in the interest of moving on, I'd like to ask people to write down their questions and save them for the gather session. That's okay. I'm sorry. We're just so grossly over time. Unless Joel is missing. Are you here, Joel?
Yes, I'm here. I'm ready to
Right,
share.
you're on.
Okay. Okay.
Thanks, Masaki. Sorry, we should thank.
Hey.
All right. I'm going to assume you can see my screen okay. So yes, this talk is actually going to have some experiments, which is dangerous because I'm pretty solidly a theorist, not an experimentalist. But what made me excited about talking about a couple of experiments toward the end is that a lot of beautiful theoretical and mathematical ideas about spin dynamics turn out to happen in the lab. Some of these ideas from generalized hydrodynamics, where there are a number of experts in the audience, and a lot of people have probably sat through introductions on this before, so I decided to try to give a slightly different introduction to my usual one, because I recently got dragged into a quantum computing collaboration, and that's actually how the neutron scattering experiment that I'll talk about was funded. So this is an area where we've worked for a number of years, and I'll be flashing up a lot of things as we go along, but I will try to get done in 30 minutes. The people who are currently at Berkeley are the ones in red. That's my student, Nick Sherman, postdoc, Maxime Dupont, and student Tessa Cookmeyer. But plenty of the other people passed through Berkeley and have now gone on to nice things elsewhere. So the normal introduction I give is what are new kinds of hydrodynamics at long time and space scales that come from quantum mechanics, so different from a classical fluid. And that's still pretty much why I'm interested in these problems. But it's nice that in a couple of different ways, and I'll talk about one in a little bit of detail and the others not, there is evidence for these new hydrodynamical regimes. If you've been paying attention, there's a lot of evidence for, say, electrons, charge degrees of freedom. I'm going to talk about spin degrees of freedom. But then a different way to motivate the kind of thing we're doing, and in particular, neutron scattering on crystals, is to ask, what are the first materials problems we're going to solve on a quantum computer, and how will we know that they've been solved correctly? So I'm mostly going to talk about one spatial dimension till the end, and a lot of the world leaders in this are on the call. I will point people who want to learn more about the field to a nice recent review that has a ton of references. I will cite, a couple of key things that were essential for what we did. It would be impossible in one talk to cite all the neat work over the last, even just over the last 5 or 6 years in this one-dimensional hydrodynamics. So I'll just try to get across the basic idea. And I will talk a little bit of news in 2D, which I think is sort of the frontier, especially for the computing aspect. So the idea is, suppose in the near future we have 100 or so reasonably good qubits. So what are you going to do with them? You can't actually factor large integers very well with 100 good qubits, if good means not great, because the factoring problem is very sensitive to noise, and we're not at a stage yet where a lot of the computer science quantum algorithms that would actually be useful for something are feasible. So there are problems like quantum dynamics is actually maybe the very first, which is what I will talk about, that are well suited to quantum hardware, and where the physics based on the experiment I'll talk about is a little bit robust. Some tiny bit of imperfection or noise does not immediately spoil it. But there is one advantage that the computer science problems have that some of the materials problems don't, but where it's good if you have a $1 billion neutron facility. So if you're doing factoring, if someone comes and tells me, these are the integers that are the factors of some 400-digit thing, I can multiply them very quickly and know if that person is telling me the truth or not. And if they're telling me the truth, then I invest in their startup or whatever. With materials, it works a little bit differently, right? Because computation is sometimes a black box. You get an answer and you have no immediate way to check it. And that's sort of true for complicated materials like high temperature superconductors or whatever. But there are cases where we can solve problems on a classical computer well beyond the diagonalization limit of 30 qubits or so. And that's one selling point of the kind of one-dimensional physics I'll talk about. And then in higher dimensions where we can't solve it on classical hardware, we can at least compare it to neutron scattering as kind of the acid test. It's like the physics equivalent of gas phase spectroscopy for quantum chemistry. So I was involved in a DOE roundtable on all of the materials problems that will someday be solved by quantum computers. I think non-equilibrium is a big one, and spins are a big one. And I'll explain why those two in particular, I think, have a lot of near-term promise, and then we'll get to the actual physics very soon. So the example of something that we can study well beyond the diagonalization limit is the kind of spin chain that appeared toward the end of Masaki's talk. So this is the XXZ spin chain. Let's ignore the magnetic field part for now. And it's been known since '92 that you can get very accurate information on the ground state of this problem. And with various improvements in the last 28 years or so, we've gotten a lot better. In one dimension, people can do finite temperature, dynamics, various slightly longer range interactions, and so on with this general class of methods, matrix product states. 2 dimensions is harder, although I will show some 2-dimensional results toward the end. But these matrix product states that underlie the DMRG algorithm, which is basically just allowing a lot more variational parameters if you want, and yet still being able to find a minimum, at least in 1D. This is very powerful for capturing most of the states that come up in condensed matter. So I'm not going to make this a DMRG tutorial, but that's the kind of state that is being built by what we do. So that's the numerical stuff I'll show. So now let's get to theoretical physics, what we're mostly here for. And that is one of our basic ideas that we use a lot is that the thermodynamics of most large systems eventually becomes a Gibbs ensemble with a couple of conserved quantities, maybe energy, particle number. If you're in a fluid, maybe momentum. There are other things that happen. We could have many body localization where we never get to that thermal ensemble, or the process by which we get to the thermal ensemble, that's kind of hydrodynamics, that could change. And in particular for integrable systems, which have a lot more conserved quantities, the Gibbs ensemble is not the natural endpoint. It's the so-called generalized Gibbs ensemble. You could ask whether that is stable to reality, either in the computer or in the lab. And then I will talk about higher dimensions. So other possibilities aside from ordinary hydrodynamics taking you to the Gibbs ensemble. What do I mean by ordinary hydrodynamics? So the reason why there are 3 equations in ordinary hydrodynamics is that there are 3 conservation laws. The first one, continuity equation, is particle conservation. Then there's momentum conservation. Then there's energy conservation. And you can obtain these by integrating over momentum in the one particle distribution function that appears in the Boltzmann equation. But this is less information than the Boltzmann equation. You lost information by doing those integrals. I'll come back to that in a second, but hydrodynamics is how local equilibrium becomes global equilibrium. So now we go to that XXZ spin chain, for example, and there are all of a sudden infinitely many conserved quantities, which are just, we thought, collections of spin operators where you've got one with 2 spins in a row, one with 3 spins in a row, and so on. It turns out that There are additional conserved quantities as well, which is a very beautiful and interesting story that I don't have time for. But let's just start from the idea that there are an infinite number of conserved quantities in some models. How is their dynamics going to be different as a result? So a clear difference is that instead of the Gibbs ensemble, we should treat all of these quantities on equal footing, and that's the generalized Gibbs ensemble. But that's actually maybe not even the most interesting part of the story, the final state. There's been kind of a renaissance where there's a sort of semi-classical or long distance description of these quantum spin chains that lets you solve a lot of things. And I think the renaissance was sort of triggered around 2016. So the quick key steps, and I'm going to go through very quickly because I want to get to the new experimental stuff. I just want to give a physical picture of why a simple single equation covers all the hydrodynamics with infinitely many quantities. And actually, this is kind of known in classical integrable systems. It's the same form of equation as you get in like the nonlinear Schrödinger equation for a dense soliton gas. And then the second question would be, does it work? And by this point, it's pretty well established that in kind of hydrodynamic limits, it does work very well. So what the way I think of this kinetic equation, again, written down in various contexts, both classically and quantum, is that you don't have real collisions. And I'll remind you of why. There's no right-hand side in the Boltzmann equation, which is normally two particles come in with two momenta, and then they go out with two different momenta. Instead, there's only a streaming term. But the streaming term is odd, weird, not mathematically odd, in that the velocity of one particle depends on how many other particles there are at that point in space-time and their momenta. So there's kind of a self-consistent velocity functional, and this is the hard thing that you have to get out of beta ansatz, but it's not impossible. And this picture of what's going on, in other words, it's like being at the March meeting and you have to get to a talk in the old in-person days. You have a place you want to get and you keep seeing people and stopping to say hi, but as long as you're not directly talking to someone, you keep steadily moving along. Because that's the way that quasi-particles move in integrable systems. So in the left-hand picture here, it is solitons of the nonlinear Schrödinger equation, but the same thing is true for beta ansatz quasi-particles. The idea of that beta Boltzmann equation, as we and maybe nobody else likes to call it, is that you've got two solitons, say they pass through each other, they retain their identity though, but they do slow each other down, and that's this interaction. So, okay. The maybe deeper fact kind of hiding in the background is that normally the Boltzmann equation, as I said, is different from hydrodynamics, or different from those three equations I wrote down. But now they're really equivalent because now, and the simplest case to write this down is the Bose gas with delta function repulsion, where the conserved quantities, at least ideally, are kind of simple. Now, if you know all the conserved quantities, that's equivalent to knowing the full momentum distribution, because it'd be like knowing all the moments of the one particle distribution, and that's basically knowing the distribution. So instead of hydrodynamics and kinetic theory, the Boltzmann equation being different things, they're actually kind of the same thing. And this even works for XXZ, where the charges are much more complicated. So I'm gonna, there are a couple of comments there for experts. Let me just now convince you that this is not just words and that it actually works. So the claim is that, sort of analogous with normal hydrodynamics at the top, if we've got an integrable fluid, some initial state will rapidly reach local GGE. That's like in a normal fluid, some initial state will rapidly reach local equilibrium. And then hydrodynamics is the much slower process by which local equilibrium becomes global equilibrium. So now local GGE is moving around in time, and we've got some flow on the space of local GGEs. And the good news is we can compare that to the numerical methods I talked about, and it works really well. So there are two curves lying on top of each other. One is DMRG, this parameter-free numerical method. The other are predictions from that beta Boltzmann equation, which we did some work to develop, practical solution techniques for various cases. And it agrees really well. So the only problem is, this is a beautiful numerical experiment, and you could in principle do it. So just to explain what's shown here, this is like you've got an infinite one-dimensional XXZ chain. At t equal to 0, you heat it up the middle. So the vertical axis is energy density. You heat it up the middle, the energy spreads, you watch it in time, and it spreads the way it's supposed to, in the sense that the microscopic numerics agree with the hydrodynamics. So that's great, but that's kind of a hard experiment. You'd need to shoot a laser and have kind of atomic scale energy resolution to see it. So we got particularly interested, this is, zooming in, that the fit is indeed pretty good for government work. you know, you could ask, okay, what about the real world? You know, what's an experiment that's already out there that you could do? And there's one experiment that's out there on the Lieb-Liniger gas by Bushul and Dubai, I think. But what I want to talk about is a different one, which actually realizes what I think is the most interesting universal prediction maybe to come out of this work on integrable spin chains. And I'll talk about the history of that in a moment. But what I want to focus on is that, you know, getting away from atoms, actually in real three-dimensional messy solids, if you do neutron scattering on one of the classic spin chains, you can see a remarkable behavior which is connected to the famous Cardar-Prisiang equation of classical physics. I think I'm going to go through part 2 pretty quickly. Part 2 is about, you know, in the real world where maybe you don't have perfect integrability, can we study things in a controlled way? And I think the answers from that are pretty interesting, but I don't know that I'm going to have time to get through it. But the main point I want to get to is this KPZ stuff. And there.
Can I interrupt just for a sec?
Yeah.
Yeah. So I'm a little, so, you know, you have, if you have an integrable system, you have, you know, quasi-particles that are the true eigenstates of your Hamiltonian. And presumably these are the ones that you're talking about when you talk about collisionless Boltzmann equation. And so you can write down a distribution function for those quasi-particles. But, you know, my understanding is there's still a complicated connection between a distribution function of those quasi-particles and the distribution function of, you know, some local observables, distribution function of local, maybe not true quasi-particles. And so I just want, can you just elaborate a little bit on that?
That is sometimes called the form factor problem. Yeah, for example, so this formalism that I'm talking about is most natural for problems involving densities. Like you've got energy density, you've got spin density, how does that move around? It has actually given some new insight even into traditional spin correlation functions. And I'll give you one example of that in a second. So I think my answer would be, and you know, Marco or others are welcome to comment. I don't think anyone can claim that the form factor problem of relating the quasi-particles to the microscopic spin is solved in some general way. But we do understand, you know, dynamics of densities of spin in kind of hydrodynamic limits where many quasi-particles are involved. And actually even a statement about universality of normal spin correlations is going to be modified by integrability on this slide.
Okay, thank you.
Sure. Yeah, so the idea I'm going to talk about came out of a couple of papers by Znadaric and collaborators. And it's a very neat idea that I didn't believe it when I first heard it. It sounded too good to be true. And you know, now I've spent a year plus working on it, and I think it's true. And what they said based on originally numerical studies, and I'll say a little bit about later theoretical support, is that if you look at the dynamics of spin flips, say in the Heisenberg spin chain at infinite temperature, something remarkable happens, which is that the spin behavior is not diffusive as you would have expected. In general, maybe for a spin system at infinite temperature, it's not ballistic, it doesn't move freely. Instead, it moves super diffusively, somewhere in between. And there's a famous example of super diffusion. I mean, there are different kinds out there, but maybe the most, I don't know, universal of them is this Cardar-Prisiang equation behavior, which originally came up in the context of that equation I wrote there, which is, you could think about it as a interface in one dimension or a height h. There's a diffusion part. I'm randomly driving the interface, that's eta. And then there's kind of the leading nonlinearity, that delta h squared. And this was sort of one of the greatest hits of soft condensed matter back in the late 80s, I guess. And it is now a very well understood universality class that appears in a ton of classical systems. Why it should appear in a spin chain at infinite temperature, there is progress on, and I think, you know, Sarang or Roman would be able to say more the progress in the last year or so, but I guess I think I knew it up to then. But there is also experimental progress. And let me just tell you, you know, how to turn this into an experimental prediction that you can look for. So the idea is that maybe, you know, maybe you don't even have to go up for infinite temperature. Maybe at finite temperature and in experimental conditions and in doing something with S of Q omega, you could see evidence for Cardar-Prisiang behavior. So the idea, so now is when we kind of started talking to experimentalists. Alan Tennant in particular is kind of one of the kings of spin chains and did work on these things a long time ago. Potassium copper fluoride is a three-dimensional model Heisenberg system. I won't get too much into crystal details and temperatures and things like that, but the prediction would be that the way that excitations scale in S of Q omega, which I don't think I defined, but it's the spin structure factor. It's like the real space, real time spin correlation function Fourier transformed. That's what neutron scattering measures. Can you see that? And can you see in particular that the way spin moves at some finite temperature, and it works best when T is of order J, there's only one interaction in the Heisenberg problem. Can you see that S of Q omega looks like what Prisiang would tell you? So there's numerics now from the folks in Slovenia and from us and so on that is actually the full KPZ scaling function. Here we're just focused on that Z equal to 3/2 exponent. And the way the calculation is done is to use those matrix product state methods at a variety of temperatures and a variety of Q, and this is integrated over omega, and lie it on top of the neutron data. So the black curve is R, that is to say, Nick and Maxime's matrix product state data. The colored dots are a lot of neutrons. And then there's the best power law fit. And the numbers hop around a bit. It is the real world, but they're a lot more consistent with Q to the minus 1.5, which is the Prisiang behavior, than with either diffusion or ballistic behavior. And the reason why this is nice from my point of view is, this is really happening because of integrability and isotropy. And yeah, certainly the spin chain is isotropic because it's at the Heisenberg point, but the integrability, there are phonons in the real world. Your spin can leak into phonons with orbital angular momentum. It's kind of amazing that it works. We do understand a bit more broadly which spin chains have this KPZ universality class behavior and which don't. Maxime and I studied a whole bunch of spin chains and said the key ingredients are integrability and, in a sense, isotropy. And that is now confirmed that at least Z equal to 3/2 by a group of distinguished theory authors, not us, Z equal to 3/2 can be understood for a variety of spin chains. As far as I know, maybe the full KPZ scaling function wasn't possible a year ago, but if it is now, that's great. I suspect it will not take long. And then
the spin rotational invariant. So what if the
that's right. For this chain, it's just spin rotational invariance. If you want, if it's easy axis, the dynamics is diffusive, and if it's easy plane, the dynamics is ballistic. And if you're willing to accept that at the Heisenberg point, which is the transition between those, it should be something in between, that would be a pretty hand-wavy argument that it might be Z equal to 3/2. If you'd like, there's a nice, argument based on soft modes in the problem by Veer Bulchandani, and then there are later works and so on, but this is one of the early ideas that I like, that I think you might like, Leo, if that was you asking the question, for what microscopically is going on that this KPZ might come from. But there are later papers that, this field is moving fast, and it's 21 and already 2020 may not be the state of the art, but there's one paper to kind of understand where KPZ might come from. But it might be under, some of the, whether there's like a falsifiable test between different pictures, I don't know.
Thank you.
So now we come to one that I think I will skip over, but it's just, the next section was going to be about, in one dimension, what if you're not perfectly integrable? How do things move around? And you get a different source of superdiffusion. And I'm just gonna maybe explain what that source is, because I think it's actually general and also will be seen in experiments. And then I'll close with a couple of comments on 2D. So the idea, if you want our favorite model system for a real one-dimensional metal, what we sometimes call generic Luttinger liquid, is to add a staggered magnetic field, which breaks integrability. But if you're in the right region of the XXZ chain, it is an RG irrelevant perturbation. In other words, and this is some very nice work by Christoph Karasch back when he was at Berkeley, you can trace out an RG trajectory that are all asymptotically the same Luttinger liquid. But that's only in the long energy limit. There are irrelevant integrability breaking perturbations at any finite temperature, and those give you a finite conductivity. Conductivity actually diverges as T goes to 0 in these generic Luttinger liquids. And the picture on the right is kind of confirming that you have indeed broken the integrability. So this is the power law divergence of the conductivity from irrelevant integrability breaking perturbations in real Luttinger liquids. So what we got interested in more recently was that same experiment, basically, where you're heating up a spot and watching it expand. except now instead of being integrable, you're almost integrable. You're integrable in the low energy limit or in the field theory, but there are these irrelevant perturbations. And then there's a very interesting competition, which is written up in that PNAS paper if you want to know more, and that's all I'm going to say, between the integrability at zero energy and the thermalization at any finite temperature. And that gives you a different kind of superdiffusion with actually continuously variable exponents. So that's what I wanted to say about 1D. And since I know we should have the gather period and so on, I'm going to close with a couple of slides on experiments and ideas in 2D, which is a much bigger, there are many fewer things we can do in 2D at a technical level non-perturbatively. So this is an example of an open problem that people still try to understand both experimentally and theoretically. It is the nearest neighbor antiferromagnet on the Kagame lattice. And even with DMRG, there are still disagreements. I might have a slightly preferred option. But what I want to close with, as I think a case that we actually do understand just in the last year or two, is an even older spin candidate, and how I think dynamical properties are going to be the key to identifying the topology in these materials. And these are the triangular lattice Hubbard model, which is actually the first thing that Anderson used as an example of a possible spin liquid in 1973, which was a good year for me. In the Heisenberg limit, we know that this Hubbard model actually has 3 sublattice order. But if you move away, in other words, if U over T is not that large and you're close to, but not at the mod insulator transition, we don't find a spin-on Fermi surface, we find a spin gap. And we've studied a lot, and this is a PRX from 2020. I'll give you the breaking news in a second. But we believed then that in the Hubbard model, and we still believe, there is a chiral spin liquid, and it's the old kind, if you want, proposed by Kallmeyer and Laughlin. It's basically a nu equal to 1/2 fractional quantum Hall state of spin flips or bosons. And the reason why we know that is there are a lot of tricks. Some of these were pioneered by Mike Zalatel, who's a co-author on this paper, to do flux twists and things like that to understand what kind of topological order you have, at least in a gap state. Entanglement spectrum is another characteristic. So the more recent stuff, which just appeared on the archive a month or so ago, is to try to understand why that happens. Because there's now in the last year or so evidence from other groups agreeing on this Hubbard model having the chiral spin liquid in the region we talked about. So why it happens is that, and this is in the recent paper, we did numerics on spin models to try to understand what are the effective non-Heisenberg, like 4-spin or whatever, interactions between spins that drive the chiral spin liquid. And the answer is it's a kind of 4-spin term that everyone has agreed has been there as a small perturbation. But there's a way to rewrite the 4-spin term and understand why it drives chirality. And that is this messy polynomial on the right side. But basically, if you can exactly rewrite the 4-spin term in terms of powers of the scalar chirality, you see that it has a negative energy minimum at some non-zero value of the chirality. And that problem we kind of know, like in other words, it spontaneously breaks chiral order to have chiral order. And that is a Kallmeyer-Laughlin quantum spin liquid because it's very close to the known parent Hamiltonian for the Kallmeyer-Laughlin spin liquid once you break the chiral symmetry. So now the dynamical question is, how do you prove that it's a chiral spin liquid? It could be neutron scattering, could be other stuff. I think edge dynamics are very interesting, and we're sort of working on that at the moment. But I think dynamical probes to identify these neutral spin liquids are going to be very important. There are other candidates. I didn't talk about the famous Kitaev spin liquid possibility in ruthenium trichloride. The basic problem is that a lot of the standard probes that are not as dynamical get contaminated by phonons or whatever. So there need to be clever ideas to see these neutral spin liquids, but I do think they exist. And then the last slide I was going to flash up is, I won't even say much about. It's a collaboration with Norman Yao's group at Berkeley and one of our organizers, Chris, which is another beautiful experimental spin system that I hope people will care about. This just appeared on the archive. The idea is that you can get very beautiful data on spin dynamics in an ensemble of nitrogen vacancy centers in diamond. And there are very unique ways that that system is different again in terms of having other hydrodynamics than what we're used to. It's largely different because of disorder. It's a little bit different because the interaction between these spins is long range. We think most of the dynamics is in a sense, describable by a classical model, but you wouldn't have written down the right classical model if you didn't know quantum mechanics. So this is, I think, quite an interesting emulator type system for new kinds of spin dynamics. And there, yeah, if you want more, you'll have to read the archive. So that's where I think I should wrap up in the interest of time. So the main point is, ballistic, thermalizing, localized, those are not the whole world, especially not in one dimension. And then in future directions, even in 1D, I think, we're very happy that this KPZ dynamics is real in the lab in spin chains. That's a beautiful idea, and it does seem to work in the lab. I think there's a lot of work on, near integrability, other questions in integral models and so on in 1D. And then in higher dimensions, I guess the main takeaway I had was, I think if you care about either spin liquids or the lattice fractional quantum Hall effect, there is going to be, I hope very soon, evidence experimentally for this triangular lattice Kallmeier-Laffont state, or in general, neutral spin liquids. Maybe you prefer ruthenium trichloride, that's okay. But I think we need better dynamical understanding of spin liquids in order to interpret all the data that's coming up. So I think I better stop there. And thanks again to the organizers for the chance to speak here.
Thanks. Questions? I think Masaki has his hand up.
Actually, I just cropped, but I do have questions.
Oh,
so, yeah. So my question is, so this appearance of KPZ universality graphs looks very, very interesting. But yeah, I'm not the expert on this KPZ, but if I understand correctly, as you said, this KPZ universality class appears in many classical systems. But according to what you said, you in XXZ chain, you just find KPZ in XXZ chain at the Heisenberg point or something.
It's just at the Heisenberg point. And in fact, yeah, I could say, I mean, if you took the classical, what I mean by saying it results from quantum mechanics is that if you took the classical Heisenberg chain of unit vectors, you would get diffusion with log corrections. And someone may call me on it. It's not precisely diffusion, but it's almost diffusion. It's still z equal to 2 rather than z equal to 3/2.
I see, but in quantum case, this KPZ appears exactly at the isotropic point.
That's right. I think everyone believes that if you move a little bit away in either direction, and actually we know,
then very roughly speaking, it seems that KPZ universality class is unstable against some relevant like perturbation. If I'm not sure if I can understand this in terms of RG.
Actually,
RG.
Can I ask a follow-up? Maybe this will clarify. So far the statement was made about the spin half dynamics at the Heisenberg point at infinite temperature. Is that correct? That's where the KPZ is found.
Actually, I think at long time it will happen at any non-zero temperature, and we just
that's fine.
We just posted a paper yesterday on that. Yeah.
So, do you expect that spin 3/2 will have the same dynamics?
Not at the naive nearest neighbor point, but you can find, there's a whole universe. Okay, so you can make integrable spin chains of higher spin. You just have more couplings. For example, at spin 1, there are 2 of them. There's SU2 level.
Right.
Anyway,
they're integrable in different ways. So the assertion is that the point is that it's integrability that matters for KPZ. But my understanding is that
it's both integrability and some kind of, and what I called isotropy, what someone more precise might call a non-abelian Lie group symmetry. And that paper I mentioned by many authors, I think the first maybe Ilievsky, is that I think there are 6 authors, but it's an impressive scholarly piece of work. I think they claim to show that if you have integrability and a non-abelian Lie group symmetry, that is enough to give you z equal to 3/2. It doesn't fully prove like the KPZ scaling function, but it does prove superdiffusion.
Thank you.
And yeah, at least there may be authors on the call, so people can correct me, but I believe that's right. Markus has his hand up, I think.
Yeah.
Yeah, Jorge, very nice. So could you state again which quantity exactly behaves like KPZ? Is it spin density actually?
In that experiment, it's just S of Q omega, the neutron spin structure factor is what they usually call it. So if you want...
so that's the equivalent of height then, or?
So the scaling laws in it are like correlation functions of the height in having the same power laws. I mean, there's a bit of a mapping of scaling functions, but basically, KPZ has this famous 3, 2, 1, 3 exponents that appear, and that's true here as well. So, I mean, I don't think, okay, I think that everything in the long time, long space limit in S of Q omega is related to something in KPZ dynamics is probably the way I'd put it.
Can I offer like a slight addition to that? So in 1D, KPZ is related to the stochastic Burgers equation and the Burgers field is the derivative of the height field in KPZ. So the Burgers field is the Z component, or some components of spin. It's the conserved density in the Heisenberg model. That's the precise mapping.
I should have said derivatives of the height because the height is shifted very.
Right.
All right, any more questions? See, I didn't get a chance to note like this extraction of the 3/2 exponent. Were there decades of scaling involved, or was it just kind of?
There is a decade.
Right. It went by a bit fast.
Yeah, so it's not, it's not the lambda transition in helium, but here it is.
Well, nothing is.
Yeah. But yeah, I mean, over some range of temperatures, it's kind of amazing that, okay, so one reason why this hadn't been seen before, people were looking in a different place with neutrons. Usually they look at, Q equal to pi instead of Q equal to 0. This is a Q equal to 0, and it's at sort of high temperature. Like usually they like to work at low temperature and see things like the spin-on dispersion relation and stuff like that. So this is actually one of few neutron experiments that is trying to be in kind of a hydrodynamical regime where it's like warm and lots of low energy excitations.
Mm-hmm.
And that's why, so we talked with Alan, and Alan said, okay, yeah, I'll give it a try as like a preliminary run, and then we'll do the serious experiment later. It turned out he was so excited about the data from the preliminary run that that's what's in the paper. There was not really, in his opinion, a need for a second run. It was clear enough after one that this was not what
so can I actually ask about that, Joe? Because it looks like, at least at 75 and 100 Kelvin, you're really fitting only 3 or 4 data points because of the error bars on, the rest of it, but it seems to be getting better with temperature.
Yeah.
But is that what you'd expect?
Well, there's a lot of, because Q equal to 0 is really bad for other reasons, right? Kind of like all kinds of disorder can pollute that.
That is exactly right. So it's, in fact, I don't, okay, if you look in the paper, we basically, and I mean, another reason is that, by the time you get below about 75 Kelvin, it's really becoming a 3D material and you're getting interchain coupling and it's starting to magnetically order. It has a non-zero 3D TC. But yeah, so I think below 75 Kelvin, I wouldn't really trust anything. So you can see the noise is getting larger for the signal reason that Vadim mentioned, and it's also crossing over to 3D. So yeah, I mean, I think the reason for viewing this as, not likely to work was 300 Kelvin, you'd worry that you're destroyed by phonons. Below 100 Kelvin, you'd worry that you're destroyed by 3D. So it's a question of, is there a window where you can see that it's not diffusion and not ballistic? And it appears that there is. Like if you look at the 200 or 250 Kelvin data, it's minus 1.4, minus 1.3, but it's a pretty good line over, as I said, a decade. It's not 2 decades, or is it? It's not 4 decades like helium, but this is what we can do.
Presumably, it's not the true Q equals 0 here, unless they've done something.
Well, this is the horizontal axis is Q. So this is frequency integrated over a window from like 0.7 up to 2 MeV. So there are different ways to take, to integrate over S of Q omega and fit it to a power law. So this is different Qs integrated.
They're probably at a symmetry equivalent point to Q equals 0, not the true Q equals 0. Otherwise, you don't get it. It's scattering. So you got to scatter.
Okay, I mean, but they're not going exactly down to Q equal to 0. But yeah, I mean, I don't know. So is your point that like Q of 0.1 is not 0.1? It's pi over A plus 0.1 or something like that?
Right.
It could be.
And that addresses Vadim's point, perhaps, about junk being in the spectra.
Well, I do know that they did say that that it gets junky when Q is too small. So I assumed it was Q actually near 0, but you could be right that it's Q near a 0 equivalent point.
I guess, did you theoretically sort of convince yourself that somehow electron phonon or spin phonon coupling is weak enough that?
I mean, it's sort of
Kelvin?
weak, partly for the same reason that it is Heisenberg. It's a very high symmetry material, and some of the like lowest order, so for example, if you ask what kind of couplings could you write down that would take angular momentum out of the spins and put it into the phonons, the lowest order ones are not symmetry allowed. So I don't think there's some absolute statement that spin is perfectly conserved in this material, but I don't think it's surprising it has a long lifetime.
And if you keep warming it, you expect to see Q to the -2? Did you see it experimentally?
I don't think they did anything above 300 Kelvin. I don't even, I think they're used to cooling things down and not heating them. And I don't know at what range you start to, melt the material or something. So theoretically, I would expect that at some point phonons kick in and you get diffusive behavior. I think that's right, well before you melt the crystal, but I don't know what temperature that is.
Can I just clarify the 1.35 that I see at 300 Kelvin? That is the to be matched with 3/2? Is that? Well,
I think, the set of numbers, minus 1.56, minus 1.34, minus 1.31, and, there are error bars in the numbers. So, it's 1 decade and it's numbers that are not exactly 1.5. The main point is it's over a big range of temperatures and it's numbers that are not at all close to 1 or 2.
1 or 2,
which are your 2 null hypotheses, yeah.
Okay, I think we should probably move on. Thanks very much. That was very interesting. Thanks. Go ahead.
Thanks to the organizers to putting together this symposium. I want to share several ideas about how hyperfine coupling between electronic spins that usually order in some interesting fashion in quantum magnets, how nuclear spins couple to them and how that can modify the physics in various ways. So what we will see is various things. So it's more of an overview than going into depth. I will show you ideas about ultra long-lived oscillations in the old compound of lithium, holmium, yttrium fluoride, and then from there go on to ideas how to use what we see there in a quantum computation scheme using rare earth magnets, like holmium is a rare earth. Then I show you that nuclear spins coupling to electronic spins can modify phase diagrams and thereby magnetic properties. And I'll philosophize about how to use that. And eventually I will sketch a few things about tuning and probing many-body localization using nuclear spins. Okay. So we focus on rare earth magnets, and that's because they have a partially filled F shell, which is very compact. That means they couple a little to phonons and they have large moments. And so they form usually good quantum magnets, and they have already a long history of quantum magnetic studies in those materials. Now, what you need to know in general is that when you put an ion into a crystal environment, the environment breaks rotational invariance, and that means the potential set up by the neighbor splits the single ion LSJ manifold, which relies on rotational symmetry. You expand the potential and you get the crystal field potential that you can expand with spherical harmonics known as Stevens operators like this. In reality, what you will get is this crystal field potential that acts in the lowest shell of this LSJ manifolds. And usually it has a form like that, minus JZ square, and then some higher order operators. And the potential essentially looks something like that. Sometimes it has a minimum close to 0. But for holmium, for example, you have a minimum at large JZ, and then you have a big potential well here. And so the lowest eigenstates of this crystal field potential is basically an admixture of 7 and then some lighter weights here. And then there's a second degenerate level, which does not couple to that first blue level due to symmetry, which is just the time reversed state. So you have an exact symmetry protected doublet in holmium, for example, with a large moment, as I said. If you take terbium, for example, you have a similar kind of potential, but here you can now couple between left and right, and you have a tunnel coupling that goes under this huge mountain, and that leads to a very tiny tunnel splitting. That is, however, important that it is so tiny, so it can compete with other small terms like hyperfine coupling later on, and we'll see that this is interesting. Okay. Sometimes or oftentimes you find minima that lie just on the JZ axis, but you can have a more complex crystal field potentials where you, for example, have 8 minima or 4 minima. And then if you switch on, so this is at the classical level of this potential seen as a polynomial in J. If you switch on the quantum mechanics, then you get hybridization and tunneling between these minima, and then you get the soft low energy manifold. And that happens, for example, in holmium gallium that I will mention a little bit later on. Okay, so in this case, when you have a soft low energy manifold that is very high dimensional, you can have a succession of phase transitions when you couple now different rare earth atoms and their magnetic moments. Then they try to align and they will start to fall along one of these minima, but that happens at lower and lower temperature. First it will align, say, along JZ, and then it starts developing a JX moment and finally a JY, and so you have a succession of tilting transitions. And this is a soft energy manifold, and so the coupling of nuclear spin to that will be interesting and can modify where transitions happen and how. Okay, so that's the basic idea. Now you add a nuclear spin that couples to the electronic spins, and that will modify the excitations of the electronic spectrum. It modifies the phase diagrams and also the dynamics. That's particularly important in the context of many-body localization. And the nuclear spin has on its own a very interesting life, and we'll actually start with something like that. So how does the nuclear spin interact with the electronic spin? It basically feels the dipolar field created by the F electrons, and that leads to a dipolar hyperfine coupling, as it is called. The coefficient is usually called A, and it's just the I dot J. I is the nuclear spin, J is the electronic angular momentum. And the typical scale for hyperfine coupling is on the order of 10 to 1 Kelvin. The strongest coupling you find in holmium ions, because you have a large electronic spin, about 8, and the nuclear spin is also large, and that amounts to 1 or 1.5 Kelvin of coupling, actually quite substantial. Now let me start and get practical. So I'll start with an old mysterious story in a holmium compound, this lithium holmium yttrium fluoride. What is that about? Well, long ago, to 2002, people looked at the magnetic susceptibility of this material at low dilution. So the holmium sits only on every 20th site. And you look at the AC susceptibility, the absorptive part and the dissipative part, and you see that the peak moves to the left to lower and lower frequency, and you find that this follows an Arrhenius law. That's actually what you expect, because you have a hyperfine activation energy to flip an electronic spin, because the nuclear spin stays the same and the electronic spin flips against it. That costs hyperfine energy, and that's makes spin flips relatively rare. And that's what you see here, essentially. So that's trivial physics. But if you look at low frequencies below this peak here on the logarithmic scale, and you pump at this frequency pretty strongly, and then you measure susceptibility, then you find that there's a very sharp and deep hole here. So you're able to, by pumping the system at a given frequency, to burn a hole in the absorption spectrum. After you pumped at this sharp frequency, you see, after ringing of magnetization for about 150 cycles, that means you somehow excite a very coherent degree of freedom in an oscillator at this low frequency of just a few hertz. And a few hertz, that's 10 to minus 9 Kelvin, way beyond any scale in the Hamiltonian. So it was a big mystery to know what could these low frequencies be and why they are so coherent? What are these oscillators? And my story will be that this is tied to nuclear spins. Okay, so what is in the Hamiltonian? You have the holmium atoms, essentially. You have their crystal field potential. You have a Zeeman transverse field often applied. You have dipole-dipole interaction, and you have hyperfine interaction with the nuclear spin. So very mundane. It was proposed already in the original paper, and then later on also by colleagues from Caltech, that these oscillators could be electronic spins that flip collectively, sort of a reversal of an Ising cluster, but that's very unlikely because the electronic spins are pinned by the nuclear hyperfine field, which is very substantial. So if you wanted to have a low energy excitation, you have to flip nuclear spins and electronic spins at the same time, and that's extremely costly in terms of matrix element. Furthermore, the large holmium moments are so big that they are far too susceptible to any internal noise. You would never be coherent for nearly a second or so. And there are hints that the involved magnetic moments are much, much smaller than a Bohr magneton, but rather a nuclear magneton. So we thought it must be nuclear spins that are themselves key players and are not only involved in pinning down electronic spins. But it's still important that the nuclear spin prevents the flip of an electronic spin. That you saw also in the susceptibility. Everything was at very low frequencies because you needed to activate electronic spins to flip. Furthermore, it's important that the electronic spins are dilute, that they are only 4%, and that suppresses nuclear spin flip-flops from one holmium to another one. If you have an excitation of the hyperfine levels, then it's hard to hop from one to the next. What is even more stable than a single holmium is a holmium pair, and we think that it's important that you look at the pairs because the dipolar field of one holmium on the other suppresses the flipping even further, and also the hybridization between the nuclear excitations helps to stabilize the system. So let's look at the holmium pairs, a compact cluster of nearest neighbor holmium. We have an electronic.
Sorry,
yeah?
Is there an exchange interaction or it's all dipole interaction between holmium spins?
At the nearest neighbor level, there is a bit of exchange interaction. It's still smaller than the dipole interaction, but
still small. Okay.
Yeah.
Okay, so it's not important.
No, it's not important for the story. No. Okay. So we look at a pair of holmium, and the idea is that the electronic spin degrees of freedom are frozen on long times and are basically spectators. But you have the nuclear spins that sit beneath them. And in the ground state, they will just be anti-aligned. And so there's nothing is degenerate, the ground state is unique. But if you look at first excited states of the nuclear spin, you can align not completely, but almost completely. And then you have two excitations, and those hybridize actually by a higher order process of hyperfine interaction and dipole interaction or exchange interaction. You can hop between this excitation and this excitation. So you expect actually eigenfunctions that are symmetric and antisymmetric combinations of these two excitations. And that gives rise to a splitting, which is still in the megahertz regime and far away from the hertz regime that we saw in the experiment. But what is now very interesting is that the antisymmetric wave function here couples extremely badly to phonon decay. So this will essentially almost never decay back to the ground state because of symmetry reasons. So this is an extremely long-lived excitation, this antisymmetric wave function. The symmetric one will decay relatively rapidly and is dephased very quickly. I mean, at least on the second scale. But where is then the coherent two-level system that we need to explain the whole burning? There is only one state here. The answer is that you have to look at hopping of such an excitation to another pair of holmium. So we now consider two holmium pairs, exactly the same geometric relationship to each other. And we look at one excitation, this antisymmetric state, and then another holmium nearby in the ground state, and the other kind of excitation where the antisymmetric wave function sits over here. And again, you have a hopping process that goes from here to here, mediated by two hyperfine interactions and a dipolar interaction. Now, if you estimate what this tunnel splitting is, then you see that this comes to the order of what the frequency in the experiment is. And indeed, if you think about this kind of state here, which is a delocalized entangled state of hyperfine interaction, hyperfine excitations, you have a highly coherent two-level system that is extremely hard to dephase. So it's very likely that this is a good candidate for what was actually observed in the experiments. Now you can ask, well, there will also be a third and a fourth pair here, and why don't I get just diffusion when I can hop from here to here? Well, the answer would be that you don't hop between any two pairs, but you have to look for resonant pairs that are in energy within the tunnel splitting, and that's rare. And so basically, typically you only have pairs of pairs that are resonant, and then they are isolated in the desert. And so you get localization of these kind of excitations, and you get sharp localized hyperfine excitations that could explain what's going on here. That awaits experimental confirmation, but we are very excited about potential future experiments that would test this idea. Now, this was the first kind of story. Whether this explains the experiment or not, it's an interesting idea to think about such kind of excitations and this very long-lived kind of hyperfine excitation that could be useful for something else. In particular, we can
ask a quick question, Markus?
Yes.
So in this picture, you're right. In this picture, is it straightforward to eyeball the matrix elements for, you know, exciting this with just external field, or is that a calculation that needs to be done?
It's a bit well, it's not particularly difficult, but I cannot walk you through the matrix element.
Okay.
But it's relatively straightforward. Yeah.
Yeah.
Okay. So we see that certain hyperfine excitations have an extremely long lifetime. So you ask naturally, can you exploit this quantum coherence in electronuclear spin complexes for something? And indeed, if you think back to the 90s, the oldest scheme proposed for quantum computing was based on nuclear spins, actually, rather in quantum dots, as far as I know, than in rare earth systems. But what we proposed recently was that rare earths are actually a promising platform, and there are several tricks that you can use to get efficient gates and a good quantum memory. So what you need for a quantum computer is a good quantum memory, and then a good active qubit, meaning you want to pass very quickly from the memory to the active state in a simple and fast manner, and then have an efficient coupling between two active qubits so that you can do a 2-qubit gate. Okay. In practice, you have to look for single rare earth ions with an appropriate hyperfine and crystal field structure that does the job. And in a nutshell, our proposal looks as follows. The quantum memory would be a nuclear spin that is well protected by a polarized electronic spin in its ground state. So if you think about the holmium example before, you would polarize the holmium spin, the electronic spin, in a certain direction, and the qubit, the quantum memory, would be a nuclear spin state, a pair of nuclear spin states quantized by this electronic spin. That's very well protected from dephasing. And now when you want to act on your quantum bits, then you have to activate that. That means you transfer the quantum information from the nuclear spin down here to an electronic spin in an excited doublet state where you have electronic magnetic moments, which are much, much bigger than those of the nuclear spin. And now these activated spins, you activate only 2 at a time, can now interact with dipolar interaction, which are substantial and go over a relatively long range. and you let them interact over a timed interval such that you can carry out a fast C0 gate, for example, with high fidelities, because you are actually very quick in activating and carrying out this gate. After the procedure, you deactivate again and put your quantum bit again into this passive state. What is interesting about this proposal in particular is that you can do gates without further engineering at relatively large distance, not just between nearest neighbors as in most other proposals. The role of hyperfine interaction is quite interesting here, so I spend a little bit of time here. So the quantum memory again is a big spin like the electronic spin pointing in one direction, and then the nuclear spin being in one of two states down here. And when you want to activate, you now want to transfer this information from this two-level system in the nuclear spin to the electronic spin in an activated crystal field level. Okay. For that, you need to work now with non-Ising doublets. So holmium would not do, but you need a state that has a different orientation of the electronic spin in the activated state here. And that is because you want to have a finite matrix element go from this state with the anti-aligned spin to that state with the aligned spin. If you add just Ising doublets, then you can basically not have such a transition. But by having a general anisotropic doublet, you can do that, and then it becomes a direct and fast transition, which is sort of directly helped by the strong hyperfine interaction. So you really make use of the strong interaction between nuclear and electronic spin to do that. Now, so far we talked about coherence of hyperfine interactions or of excitations and how to use them. But you can also use nuclear spins for just thermodynamic manipulations, namely nuclear spins modify the thermodynamic phase diagrams of various materials. And if that is the case, then you may have the dream that by controlling the nuclear spin somehow, or if you think of switching it off temporarily, you could move the phase boundaries, because it depends actually on the coupling to the nuclear spin, what the electronic spins do, and thereby switch between magnetic phases. So if you had a knob that allows you to sort of knock out the nuclear spin by sort of doing a pi/2 pulse and turning the nuclear spin basically perpendicular to the electronic spin, you would do as if the hyperfine coupling is switched off, and thereby tune the phase diagram to a different topology, and therefore you could switch between states. So that nuclear spins have an effect on the phase diagram of materials is again very well known from the lithium holmium fluoride case. Here's the phase diagram. You have the ferromagnetic phase and the paramagnetic phase, and you see at low temperatures of the order of the hyperfine scale, you get an upturn of the order. That means that nuclear spins, by coupling to the Ising moment, they stabilize them, they suppress quantum fluctuations, and therefore the ordered phase is growing here, and this is extended. So that's the easiest case of seeing that nuclear hyperfine coupling can affect the phase diagram, and in particular it can extend the stability. That's not so particularly interesting, because if you switch off the nuclear spin effect by randomizing the nuclear spins, what will happen is that you just go from an ordered phase to disordered phase, and that's usually not so much what you like to do. But it could be interesting if the disordered phase was, for example, a topological spin liquid, then that would be a very interesting thing to do. You could think of a spin liquid that is almost spin liquid, but not quite yet, and it's ordered, and then you kick off the nuclear spin, and then it becomes a spin liquid. That would be very interesting. However, the disorder that you create is essentially the same as if you did heating, and therefore it's a bit hard to know whether you did actually something interesting in controlling the nuclear spins or whether you just injected energy, right? What is a more interesting situation maybe is if the nuclear hyperfine coupling actually turns down the phase boundary like that, such that you have a re-entrant phase boundary. That means the hyperfine interaction destabilizes the order here, but if you heat the system or if you destabilize the hyperfine interaction by temperature, then the effect of hyperfine interaction goes down and you get back to an ordered phase. Okay, so now imagine that you start here, where in the hyperfine coupled case you are disordered, but now you somehow manage to turn off the nuclear spin effect, then you're back to an ordered phase. So by manipulating the nuclear spin, you would induce order. The same thing you can do by heating, which is also an interesting effect. Heating is relatively simple, but if you induce order by doing so, it's an interesting thing to do. A third possibility might be that you destabilize the order by hyperfine coupling, but that the temperature effect is not like here, but the opposite way. That's a bit exotic, but I think it can happen. And if you have that, and you switch off the hyperfine effect, then you would be in the ordered state. But if you heat, you would not get the same effect. So you would have a way to tell whether you really control the hyperfine interaction by some manipulation or whether you just heat, which has two different effects. That would be conceptually interesting. But now the fundamental question is, can you ever have this really, and what do you have to do? Well, the answer is yes, you can, but it's not all that cheap to get it. So the first thing you have to realize is that hyperfine interaction always prefers to an order along the easy axis. So if you have an anisotropy of your moments along the axis, hyperfine interaction always wants the spin S to point along the axis with the largest G. So what you have to look for if you want to destabilize magnetic order, then you have to find the material that orders along a hard axis and not along the easy axis. And can you have that? Yes, you can. For example, in dipolar magnets, you could also look at holmium-gallium that I mentioned previously, where you have this soft energy landscape with the many tilting transitions. That's interesting because it contains holmium, where the hyperfine coupling is very strong. Or you could look at heavy fermions, which also have hard axis order. But let me explain to you the dipolar case. So you just have spins sitting on some lattice, say a trigonal lattice with dipolar interaction, and you look at the phase diagram. So you have an anisotropy of the single ion spin, the G alpha, and you have, of course, lattice spacing C and A. And now you know that spins like to align. If you have a pair of spins alone, then and you put them together, they like to align. So if you have very anisotropic lattice spacing like here, where the C axis is much smaller than the A axis, then the spins like to point in the C direction. Here, where the shortest lattice spacing is in the plane, the spins like to lie in the plane. And now if you make this sufficiently extreme, then even if you have an anisotropy that would favor the opposite order, so if GZ is bigger than G perp, then you would actually want to prefer this. But if the dipolar interaction prefers this, then there's a region where you order against the easy axis. Okay, so here we are in a sweet spot in these two regions that are hatched, where the hyperfine interaction prefers something else than the dipolar or spin-spin interaction. Sorry. So here you get the candid phase actually. Sorry, there's something wrong. Now, if you take a material like here and you look at the temperature and longitudinal field phase diagram, you can undo the the counting by pushing sufficiently along the z direction, and then you have a phase transition here where the counting sets in. Okay, and the order is transverse to this field. Now you can ask what happens if you add the hyperfine interaction to that. And as we expected, this should be a case where hyperfine interaction destabilizes the order, the counting order. And indeed, when you do mean field theory for a three-dimensional system, you find that the phase boundary is now re-entrant. That means if you go close to this phase transition here, a quantum phase transition there, and you manage to control your nuclear spins, you induce a counted order from a non-counted order. Likewise, if you heat up the system here, you get a transverse order. So that's a pretty neat effect of hyperfine interactions, which is more interesting than just stabilizing an order. Now, finally, I would like to tell you that you can not only tune thermodynamics, but you can also tune dynamics. That's more of an outlook or an advertisement, but I think there's a nice story to come out from our experimental friends soon. So of special interest in random magnets, in doped magnets with rare earths, is the topic of many-body localization of spin dynamics. Many-body localization means that there's absence of thermalization due to disorder which is stronger than interactions. And if you manage to get that, that's always good to enhance your coherence in the system. So a canonical model for many-body localization is sort of a couple two-level systems, Ising spins, for example, that interact, and then you have some randomness and you have some transverse fields, right? That's basically the simplest thing that you can write down. We have interactions, randomness, non-commuting terms. The regime of interest here is where the randomness in this term and this term are of the same kind of order as the interaction. Then you have an interesting competition. Now it turns out that this kind of model is exactly realized in dilute and in the dilute dipolar Ising magnet with, instead of holmium here, you take terbium. If you remember from the beginning, the terbium has a level structure that is a slightly split doublet. Then, so it has a crystal field splitting, which however is very small. It was only 1.3 Kelvin. And then it has dipole-dipole interactions between these near doublets, which is proportional to the concentration of terbium because it's dipolar interaction. And then there is disorder here, and the disorder has an interesting structure. So crystal field splitting first is disordered because you have usually strains in your material. But what is really interesting is the structure here of the random fields. Why is there a random field? Because, well, you have the external field that you may apply, but then you also feel the hyperfine field from your nuclear spin. And the nuclear spin is conserved because there's only Iz in the Hamiltonian, and so this is a quasi-conserved quantity. But for each terbium, it's either plus or minus 1/2 or plus or minus 3/2. And so it's a quasi-static discrete disorder, and it defines 4 species of atoms that sit in your material. What is now interesting is that the magnetization of the local eigenstates of just this term here is proportional to this field here. This field divided by the crystal field splitting, and since the crystal field splitting is small, this is appreciable. Okay, but the important thing is that if Hi, this combination here, is 0, then you have 0 magnetization. And this magnetization is important because that couples to surrounding nuclear spins like from the fluorines, and that controls how much disorder these local degrees of freedom see. So you have a knob to tune the disorder just by working with this external field here. If you adjust the external field to one of these values here, then you reduce the disorder for that particular species considerably. And that means you can tune the disorder, at least of one of the species, by tuning the external field. On the other hand, you can tune the interaction strength by playing with the dilution of your rare earth species. So you have a wonderful system that realizes essentially the canonical model of MBL, where you can tune disorder and interaction, therefore trace what is going on. And we are...
Markus, can I ask?
Yes.
Sorry, just wouldn't there be stray dipolar transverse fields in this system as well? Why are they all in some particular z direction?
That's because of the crystal field structure of the terbium. So you have a low lying, you have two singlets, and the only matrix element that you have between these singlet states is a JZ matrix element. So there's only sigma z that comes from, say, magnetic interaction. You cannot have sigma x or sigma y terms from magnetic interaction. So this is the only off-diagonal term that you have between the low-lying two singlets. And then this term is just describing that the singlets have a certain splitting. That's a crystal field splitting. I don't know, is that clear?
So what direction is, well, I was actually thinking about the Jij term, the sigma z, sigma z.
Right, so this is the dipolar interaction projected into the space of this low-lying singlet.
So what sets that, so just whatever is the local, like at the terbium, you have some particular axis which is special.
Yeah, Z is the C axis of the crystal.
Ah, okay. Okay.
So this is the only matrix element that is non-zero within this singlet, two singlets.
So sigmas are L plus S, right? Is that what you're saying? These are the spin orbit eigenstates.
No, sorry. So you have an LSJ manifold as usual, and then you break that down with crystal fields, and you end up with two very low-lying singlet states. Singlet means just crystal field symmetry. It's a one-dimensional representation. And now you have a two-level system, and now you can ask what are the matrix elements of Jx, Jy, and Jz within this two-level system subspace. And you see that only Jz has a matrix element. It's an Ising system, and Jx and Jy have zero matrix elements in this subspace.
And the lattice actually has a C-axis, which is special.
Yes, right. Yeah, like all these lithium fluorides, the C-axis is the high symmetry axis. Yeah, and so this is the C direction indeed. Right. So this is a nice system because it realizes Ising, the Ising model basically, with disorder and transverse fields sort of for free, and then you have these tuning knobs. Now we are looking at that, and we are analyzing spin echo in here, and that means you create local excitations and then you measure their coherence, and by doing so you sense the suppression of fluctuations and spin dynamics by disorder versus interactions becoming bigger and bigger. And you see definite traces of many-body localization now in a real solid magnet, coming along with a lot of other interesting many-body physics that I don't have time to explain, but a paper is soon going to come out. So with that, I would like to summarize this review of more or less of ideas. We saw that nuclear spins and nuclear hyperfine excitations can be highly coherent objects, and in particular, they don't need to sit on a single rare earth, but they can sort of delocalize over pairs and then pairs of pairs, and that are very interesting objects, and you can see localization physics there. You can also see localization physics if you tune your disorder using the hyperfine field and the external field to combine judiciously. By using the high coherence, you may have a nice quantum computing platform with nuclear spins. And what I find interesting is that you can also manipulate your nuclear spins and thereby induce order or control magnetic phases of the electronic spins. And I think that's not restricted to nuclear spins. You may have other local degree of freedom that couples to an electronic degree of freedom, but otherwise doesn't interact. And much of what I said should carry over to such more general cases. Okay, with that, I'd like to thank you.
Thanks. Questions? Or any more questions? Okay, if there are none, maybe we should move on. Thanks, Markus, again. Jorge, are you still here?
Yeah, I share the screen and you tell me if it works.
All right, take it away.
Okay, so this is work that we are doing and partly finished with Silvia Papalardi. So, okay, so our motivation was to try to understand these phenomena in which certain properties are limited by quantum effects. There are properties that classically can take any value, and quantum mechanically they are limited. So the first one, or at least the one that came some time ago, is the viscosity. There has been the idea that if you divide viscosity by entropy per unit volume of your system, this is bounded by h bar over 4 pi. So this means that your system has to be more viscous than something if it's quantum. More recently, there was this bound on the Lyapunov exponent, which was defined on the basis of a definition that was introduced by Larkin and Ovshinnikov many years ago. And Maldacena, Schenker, and Stanford proved this bound, so that the Lyapunov divided by the temperature is bounded, has to be smaller than something. And okay, the idea of these two, so I must say that this bound, the first one, I don't know what is its status. The second one is proven. The first one, I don't know exactly to what level of certitude there is. These bounds are interesting at low temperatures. This is when they do something. And what is interesting for the field theorists is that they are saturated or seem to be saturated by models of black holes. And this they find interesting. Okay, so if I go to low temperature, let us think of the bound on chaos, for example. I want the system to push as close as possible to the bound. Is it okay? Are you hearing, Vadim?
It's great. Yes.
Okay. So I want the system at low temperatures to be interesting. So this situation won't do, because you know what will happen here at low temperature. I will sit at the bottom and there's no chances I'm going to be able to have chaos. So the bound will be active, will apply, but it will be trivial. So I need something that is flattish, and multidimensional, so that I can move around and have a chance, even at very low temperatures, to do something. So systems that do this are two kinds of systems. Let's say one are the billiards. In a billiard, whatever speed you move in, you are chaotic, because essentially the trajectories are drawn on the paper. They are drawn on the configuration space, and the only thing that energy changes is just the speed at which you move in them. And another system that does the same thing is inspired by being at the bottom of the well is to directly move on a manifold that is curved. So this manifold, this is a famous review that I would like to advertise of Balázs and Voros many years ago. For example, this is for the hyperboloid, two-dimensional hyperboloid, which is a surface of negative curvature. So these systems, curved manifolds, are also systems. Obviously, temperature doesn't play a role here because here you move along geodesics. And the only thing that energy does is how quickly you're walking along the same geodesic. So these are candidates to be interesting at low temperatures because nothing in the potential, there is no potential essentially. Now, this we learned recently. In fact, Arnold, Vladimir Arnold, makes this interesting remark that billiards are just deflated surfaces. So take this Mickey Mouse balloon, deflate it, and you've got a billiard. Take an ellipsoid, deflate it, and you get an elliptic billiard, and so on. So, so Riemannian manifold are the general context that we are interested in. Okay, so let us look at it a little bit more in detail. So classically, as I said, the trajectories are geodesics. This is very easy to prove. A geodesic is a line of minimal length between 2 points. And energy is basically the speed at which you happen to be walking on that geodesic. What is the quantum analog of this? The quantum analog is that simply your Hamiltonian has all the units outside, each bar, the mass, and some length, any characteristic length. And then what you have inside, the quantum part, let's say, is just the Laplacian operator for a curved surface. This is called a Laplace-Beltrami operator, which is adimensionalized. And it is what generates the, let's say, the free waves, to call them somehow, on the curved surface. So, but we are interested in macroscopic systems eventually, although we are playing now at low dimensions, but we are interested in really thermodynamic systems. Can you make a thermodynamic billiard? So a billiard that is n-dimensional or something like that? And the answer is yes, it is very famous, the most famous of all. If you consider hard spheres and you look at them in the space of the positions of all the particles, what you see is that, in fact, the joint position of all particles is in d times n, the number of spheres, d the dimension, d times n polytope. So it's a billiard in n dimensions, about which I can tell you a little bit more later. So hard spheres are a billiard, but they are also a macroscopic system with a thermodynamic limit, etc., etc. This is something that came out essentially of 2 papers of these gentlemen, Militevsky, Subro Bhattacharjee, who I think was present, and Roderick Meusner. They recognized, or it is clear that in a surface, a system like this one, where you have that the spins on a plaquette are 0, the sum of the spins, and the spins live on a sphere, each one of them, is of course also a manifold if you are strictly without keeping these constraints. And it is, of course, a macroscopic system. The manifold is a contorted manifold because it is the Cartesian product of all the little spheres corresponding to each spin plus this constraint. So it is a tortuous manifold. So they studied this model, but in a slightly different way, in the sense that their spheres are already a phase space, which is the usual thing for spins. Instead, we are more interested, although it doesn't make an enormous difference, but for conceptual ease, we are more interested in treating the spheres as a configuration space, and on top of them have a momentum with which you move along the spheres. But apart from that, it is essentially we are working on this same system. So what happens with hard spheres? So let us look at the bound on viscosity. So classically, it is very easy to show that if I divide viscosity by entropy per unit volume, which has to do with the radius of the spheres, and by h bar, everything gets together here. And the only thing that remains is to determine some function of the packing ratio, the packing fraction. Packing fraction is how much volume is occupied by the spheres divided by the total volume of the box. So this is a-dimensional. It's a function that you have to determine, and the only dimensions are here. If you're in a classical context, this is it. I mean, this is a constant, and you get that the viscosity goes like t to the 1/2. And this violates the bound at low temperatures, which because goes to 0. So if I plot in terms of the temperature, what I see is that it's okay. This is a classical situation for the spheres until I reach a point where I am manifestly violating this bound. So something is going wrong. That point, not surprisingly, is when the de Broglie length, you will recognize it here, the thermal de Broglie length, is comparable with the radius of the sphere. So that sounds reasonable. And now you have to say what goes on here. Something goes on, quantum intervenes. For certain cases, it could be superfluid transition, which happens around there, but not for every situation. So that's not the end of the story. In any case, what happens quantum mechanically? Well, using the adimensionalization that I did before, what you can show is that quantum mechanically, it always is a function of the solution for the viscosity is always a function, and this is exact, of the quotient of the A length divided by the de Broglie length of the particles and the volume fraction, which is itself adimensional. So you know that this is a good variable to measure how quantum something is. Notice how simple it becomes. But we still do not know what goes on here. Now, Riemannian. So what do you do with a Riemannian surface? You, as I said, classically, the Hamiltonian is this one. GIJs are the metric that defines the Riemannian geometry. It's the delta, it's a Kronecker delta for the usual flat one. And particles move along geodesics. The only thing that happens if you multiply by 2 the p's, the momenta, is that you will move along the geodesics twice as fast. So the Lyapunov exponent, which is the separation of the exponential separation of 2 trajectories, is given by a purely geometric separation, which I called lambda GS, geodesic separation, times the velocity with which you move. Because if you move faster, this separation happens faster, simply because you're showing the film twice as fast. So, so then you have this purely geometric thing, which depends on the sphere, on the manifold itself. And then you multiply it by the velocity, which is basically the square root of the energy divided by f. So again, we do exactly the same thing as before. And what we get, just adimensionalizing everything, is that the quantity that is to be bounded, which is this one, is given by the thermal de Broglie length, or the de Broglie length, whatever, the wavelength of the waves, and this, which is the rate at which you get that geodesic separates. Notice that this one is only has dimensions 1 over distance. It's just per unit distance and not per unit time. So this is a distance, this is 1 over a distance, And what you get is that for a given, in terms of the temperature, as you go down, this goes up. Notice that it goes up not because the Lyapunov is going up, because it's divided by t, and here there's only a t to the 1/2. This is why it appears to go up, although the Lyapunov itself is going down. It just is saying that you're not going to 0 as fast as the bound asks you. When does this happen? Well, it happens precisely at the point where the length of the de Broglie length is comparable to some curvature radius of the manifold. So I have to say this law was verified very nicely by Roderick, Schubro, and Thomas, and for their model. Although I have to say, as far as I can see, it is not 100% a situation on a Riemannian surface, because theirs is more like a phase space, but maybe it doesn't matter. So classically, we are forced to admit that this violates a bound, and it violates it at that point. So within these systems, it's a nice place to answer. So, okay, what is quantum mechanics doing? How is it imposing or enforcing the bounds? The reason why we ask this is because the proof itself is not especially eloquent. It's not terribly difficult, the proof of Maldacena, Schenker, and Stanford, but it is not terribly eloquent as to the mechanisms that do this. So we will start with a very simple model to see some aspects. So our model is like this. It's the hyperboloid I mentioned before, the blue zone, which is the one that has been studied extensively. It is chaotic. It's a surface of constant negative curvature. Its radius of curvature, its curvature is 1 over that is the geodesic separation. And then because we want a lead, something to inject particles, we stick to it a cylinder. Cylinder is completely trivial. It's as if you moved in a flat situation, because if you stretch it, you open it up, it's the same thing. So you have a trivial part and then a non-trivial part where chaos happens. And we know a lot of things about this. We know the Lyapunov exponent that you pick up by moving in the blue region. And this thing is happening only in the blue part. So now this has been, as I say, there's this beautiful review on this. And now, by the way, the hyperboloid, this is why there is this Escher picture here, is represented by the Poincaré disk, which it's represented by the Escher mandala. So, okay.
Okay,
so
can I ask a question?
Yes.
Sorry,
yes.
I haven't, maybe I lost track of sort of the idea, but this manifold arises, what determines the manifold? I mean, if I think of one particle, then I can imagine, it's just the equal potential curves defined by the potential that it moves in.
Yes,
or the shape
of the bottom of the well.
Or the well, or the shape of the billiard or something like this.
Exactly.
But am I supposed to be thinking of that situation or something more general, like interacting?
So interacting will not generally do the job, but if you consider this system, it is clearly a manifold, no? Because you're imposing these two constraints and nothing else. So you are moving on a surface which is pure constraints, no a priori, no potential. Why do we choose these and not an interacting system? Because with an interacting systems, we risk a situation like this one, where at low temperatures, nothing interesting happens. We need that something moves even in the limit of 0 temperature.
But the proof of Stanford and Schenker and company, isn't it related? Isn't it supposed to describe a sort of a general quantum field theory?
Yes, But the point with this case is not that it violates their proof, it's that their proof is unnecessary in this case, because you just sit at the bottom and you don't have any Lyapunov and that's it. So it is only in risk of being challenged in this case, let's say, not in this one. This is why we study these cases.
I see. Okay, thank you.
Okay, so so let us see what happens in this model. So you can write this model in appropriate coordinates. I spare you the details. Notice that the summon place, this is what is telling you that you have a curvature. It's the fact that while in this case, this is a constant, tau x is a constant. So this is Pythagoras as you know and love it, but this one, no, it depends on the point. So this is the hyperboloid part and it's matched at tau equals tau x, it's stuck to the cylinder. So this is one way of parametrizing this curve, this surface. The Hamiltonian reads this way. So you see here it's p tau plus I phi, and then this is a constant. So this is usually like in the cylinder, you essentially really have a free particle. Here it is free in the sense of moving along the geodesics of the hyperboloid, but it is not straight lines, and the geodesics diverge. So you can solve this problem. The quantum Hamiltonian, again, this one is just that of a free particle because this is a constant, while here it is something strange. Let me make a clarification, which is very confusing. It's not essential, but it has to be said. This model as it is actually is integrable because you have two constants of motion. You have a angular momentum, and then the radial part is one-dimensional. So, but that is accidental, in fact. Its trajectories just go very far and come back, and they diverge, but then they retrace their steps. The point is that if you add the slightest perturbation to this, then you completely break integrability. And the interesting point is that nothing depends very much on this little perturbation that you add. This is a conceptual nuisance, but we kept it because it's so much easier to work with this that it was worthwhile. So what we do is we actually work with this plus some little thing that will spoil this perfect coming back. Okay, so that's a clarification that is annoying and it took us a while to work it out. So the particles move while they are in the cylinder. They don't have any chaos because this is almost like flat motion. Then they enter the hyperboloid. Their trajectories diverge and then they move out and again. So the Lyapunov you will have classically is just the one that the hyperboloid has, which is well known, simply multiplied by the rate, by the fraction of the time that you spend inside the hyperboloid, because this part is inactive from that point of view. So now we have this model and we can try to see what are the mechanisms. This is classical, no? But we can quantize it, as you saw. And now we look at the wave functions and we want to know, okay, how is quantum mechanics blocking? Because remember that this kind of system, if you leave it alone, as you go to zero energy, you violate the bound. So quantum mechanics has to do something. What does it do and how does it do it is what we are asking here. So first obvious reason, which is not interesting, is the mere size of the problem. If the cylinder has a size which is small compared to the de Broglie length, of course, you don't have any chaos of any kind. You just have essentially the ground state of the cylinder. So this you always have. And this is what happens with spins. If you have classical spins and you go down by h bar, you get to a point where, in fact, on the sphere, you have only the very lowest harmonics. You have a low spin system and you don't expect any chaos. So pure size is an effect of a manifold, yes, but it's not especially mysterious. So that one is okay. Now, let us move one step up in mystery. This is the Hamiltonian of the system. And now you see it has a sign here and a sign there. This is the part in the hyperboloid. This suggests we make a little change of variables and we get to this equation. Believe me, going from here to here is one line. And you discover that by effect of this hyperbolic sign, you get an effective, now this looks really like Schrödinger with this factor that depends on angular momentum. But the point is that you get this step here, which is a repulsive effective potential that comes from curvature, because you can, this 1/4 is actually the radius of the hyperboloid divided by 4. So it is actually proportional to the Lyapunov exponent, which means that your system, now you can analyze this, has a wall that is purely quantum mechanical because it's a potential that is proportional to h², but still, for the very, very low things, very low energies, you feel that this will expel you from the chaotic regions. And indeed, this is what happens. So this is a, on this side, you have the hyperboloid, on this, the cylinder. You fire a particle that is very fast, it enters the hyperboloid, comes back, and you are okay. You can have a big Lyapunov exponent because you're living nicely inside the hyperboloid. However, when you go to very low energies, this is just diagonalization. The wave along the cylinder is okay, but it is evanescent within the hyperboloid. And this, there is no potential. It's this effective repulsion due to negative curvature. It's important that it's negative curvature. And even lower energies, then no way you enter the hyperboloid. So you won't be surprised to see that these low energy wave functions are not chaotic because for them, the hyperboloid is just a wall. And this is a very general phenomenon, the fact that wave functions dislike curved regions. Okay, but now the third one is the most mysterious of all, because still I could inject particles inside here and make their energies lower and lower with respect to that step I was mentioning. And what happens then? And here comes a place where the bound appears naturally, not the bound, sorry, a number that is of the order of the bound, which is the following. I fire now 2 packets, we are semi-classical, along 2 geodesics. Essentially, this is like the old packet you studied at university, moving along a line, nothing special in that. There is an initial width of the packet. This is configuration space, it's not phase space. So there is a stretching of the packet, which depends on the uncertainty in momentum that you had at the beginning. In a certain sense, the uncertainty in momentum amplifies with time. This is the dispersion of the velocity times the time. So it gives you the length of this along the geodesic of this packet. And now when you look at how 2 things disperse, so the average disperses like a Lyapunov phenomenon, exponentially in time, as it should. But then something very strange happens, which is that the dispersion of the packet itself makes you, contributes to a certain probability of having a much larger dispersion, because this end of the packet is the avant-garde of the whole thing. So at the end of the day, a very simple calculation with a Gaussian tells you that you have 3 terms, a constant one, which is the initial uncertainty of the packet, the one you like, which is the Lyapunov, and the one you are surprised to have, which is t², which doesn't look at all like anything like a Lyapunov. It is faster though, but it is not to be, when you cannot associate it with a usual Lyapunov. And now you ask yourself, okay, when do I really have a Lyapunov? Well, when this thing is bigger than this, and this thing is also bigger than this. So I'm happy to say that I have an exponential growth, a linearly exponential growth. When you put these conditions together, and you ask that this happens around a Lyapunov time, you get essentially the units of the bound. So you don't get the 2 pi that goes here, but you do get the bound. So you only can define a Lyapunov exponent thanks to this silly phenomenon. So this is how the bound is implemented inside the manifold, a manifold that is curved. You are not allowed to even define it as a linear thing in T because of this phenomenon of dispersion, which is nothing but the uncertainty principle applied to this case. So this is cute because, okay, this is for bosonics.
Can I ask you a question?
Yes.
So do I understand correctly that it's completely classical explanation if you insist that probability distribution of a particle satisfies the uncertainty principle, right?
Yes, basically, yes. You accept this as classical, I suppose, that delta P over M, which is a delta velocity times T gives you the width of the packet. Right. It's a little bit quantum in the sense that you're talking about dispersion, but yeah, it's a very semi-classical argument, yes.
Right. Okay.
Of course, if you want the 2 pi, you have to be probably more serious. But to get a simple idea, this is uncertainty principle.
Right. Okay. Thank you.
Okay. This is perhaps my main message. Just do I have 3 more minutes?
Yes, sure.
Okay. So there's a problem though, because we want to take the bound up to 0, and we have a problem because if our thing has a wall here, well, you have a situation where you enter, you have a situation where you don't, and this is something quantum acting here, and that's not nice because it acts once and then God knows. If you want to really feel what happens as you approach 0 and have non-trivial things happening all the way down to 0, then what seems natural, and this is something it's very easy to do in this model, you connect a hyperboloid that is slightly very curved, a hyperboloid that is less curved, and then the cylinder. And so what happens is nice. You get the same phenomenon, only that as you go down in energy, first you lose the possibility of entering the place where you would have a bigger Lyapunov because you have a step. But you still can enter here, so you do have a form of Lyapunov. And then when you go to even lower energies, not even this one is accessible. So what is nice is that you are losing one by one the places. You first are greedy when you're semi-classical and want to use the more curved regions of space. But from those, you are excluded as soon as H bar is turned on. Then you turn it even further on, and then the medium ones, which were not as good but gave you some Lyapunov, are lost, and so on and so forth. We think that what happens in reality is this: the interesting cases are multi-scale, but it's just if you want a refinement of the argument before. And just to end, remember what I said about hard spheres. You can think of them as one particle of d times n dimensions moving in this polytope, which is a billiard. But one thing we know is that when the spheres are very dense, you have all sorts of lengths in this polytope. And the short lengths give you big Lyapunovs because you bounce a lot, and the longer length gives you smaller Lyapunovs. But H bar kills the shorter lengths because you don't move along them when the de Broglie length reaches those lengths. So one by one, you start losing what gives you the largest Lyapunovs, and you're left with what gives you the lowest ones. And if this process never stops because there is one direction that is infinitely long, then you would have something interesting happen all the way down to 0 temperature. And this would happen in the case of random close packing. So spheres that are almost at the level, the highest amorphous packing that they can have. So that's that. Thank you very much.
Thanks. More questions?
Oh,
There, go ahead.
Yeah,
okay.
Markus.
Oh, I think I didn't raise my hand, but Markus did.
Yeah. This effect of this repulsive barrier basically is that like a self-energy effect that you try to move into a region where your connectivity is like lower and therefore
yes. What happens is that when you're in a curved region with negative curvature, you have more directions as you move out than you have in a flat region. So a negative curved manifold wants you to go away more than a flat one. And this wanting you to go away is a bit like being in an inverted potential. So that would be the interpretation.
Yeah. Is there the opposite effect that if you have a cylinder and you end it with a positive curvature spherical shell, then the ground state sits on the spherical shell? Is that
there are, yes. It depends a little bit on how you constrain on the surface, but there's a big literature on wires that when are bended and have positive curvature, they have attractive regions where the electrons prefer to be. So yes. Mm-hmm. But there are subtleties. You have to be a bit careful on how you constrain because it depends a little bit on how you apply this constraint. Mm. Andrew?
Chris, did you have a question? Or Andrew, whoever?
Well, I guess my question was a little bit related to Markus's, which was about if you put positive curvature on the end. I'm kind of would have thought that you also eventually would freeze out of wanting to be on anything with a curvature that had a radius smaller than your de Broglie wavelength.
Yeah. But you also have problems on the cylinder itself, no? Because itself is finite, no? But yes. So the effect of exclusion, we used to believe that it was the only thing. And then we started saying, well, but wait. Okay, I have this step, but who forbids me from putting a very big step here and forcing the particle in, no? Kick it in. And so in the end, we realized that although this is present, surely, interesting regions are going to probably be repulsive. It's not the only effect. We are now more like putting our money on this kind of effect. As a general thing.
I mean, I think my intuition there is simply if I think of trying to find a low energy state in something which forces me to curve, I've got to pay the kinetic energy.
Yes. You've got to pay, and this will hamper your possibilities of getting a true Lyapunov because you are not going there.
Mm-hmm. So then I had another mini question, and then I'll look. So you mentioned deflating balloons. So
yes.
At the end, though, when you were thinking about your polytope, is it basically, should I think of it as H bars just inflating them back up?
I don't know what.
Which I mean, if you have a bunch of packed spheres and they're hard and they bounce around like billiards and you turn off H bar, then that's what they do.
Yes.
But you turn on H bar and you go to low temperature, and I start thinking of them as their wavelength gets larger than their size, and then they basically blow up like balloons and can't move anymore. They just
this would be micro balloons, and we should think how this reflects into this phase space ensemble of the entire balloons, but it's true what you say. So you, when you have so this I know from Mathieu Viard, that essentially the sizes, the omegas, the frequencies at which I can move in a diffuse in a polytope like this, they follow this this curve. So what happens is that as you tune on, as you make the de Broglie length longer, you make H bar larger, these are not useful anymore. They were the best to get the biggest Lyapunov because they have the biggest omega, but you don't go there because you cannot talk about bouncing. So you will be in the fundamental mode of many. Going back to particles, this means, yes, that the extra radius they have is not very useful. This very long thing, instead, when you look at the particles, it corresponds to collective motions of the particles that are well known, well studied, where the particles move, many of them move together in a kind of swirly motion, and those resist much more this effect of quantum. And what Mathieu and collaborators showed is that you get all the way down to 0 when you are at close packing. So you get an infinitely long one that will stay quantum for the whole temperature range.
Okay, I'm going to dive in before Chris asks another question. Very nice talk. You made a comment a few times about being interested in configuration spaces rather than phase spaces. So we've been thinking about characterizing many-body quantum chaos by projecting onto different variational manifolds.
Yes.
And I think they are phase spaces in the way in which you're using the terminology. What does that change about the sort of things we end up being able to say?
We are able to say less things, but we are willing and we would really dearly want to go to real phase space, because there's no reason to stick to what you have here, which is particularly nice, is that you have this geometric structure, and then energy only plays the role at which speed you're moving along them. But this is probably, if you knew how to play this game in phase space, it would be much better. It's just that for the moment, it's easier this way. But of course, there's nothing can, if things rely on too much on choosing configurational space, they are not nice, obviously.
Okay, thank you.
Any more questions?
There's another hand. I'm not sure who it is.
Markus has a hand, but maybe that's a holdover. Yeah. Okay, well, let's wrap up. I think this is the last talk of the last symposium. Guess thanks to all the participants, co-organizers, and speakers. All right, let's go together and have fun, and hopefully see you all in person at some point.
Let's hope. Bye-bye.
All right, thanks a lot, Jorge. All right, bye.